Hey everyone, Thrasher here. In this video we are going over the Doppler effect. And it's something that you hear, it's a result when the source of something that's emitting a sound, like an ambulance, is moving relative to some object that's listening. For example, if you're on the side of the road and an ambulance or a fire truck is passing you by, you hear this change in frequency, a higher pitch to a lower pitch. That's the Doppler effect. So we're going to look at that and where it comes from. Now, before we actually get into the Doppler effect, we're going to go over a term called wavefronts. I'm not going to write down any definitions. It's really just a diagram you need to be aware of, because when we look at Doppler effects, they use this type of diagram. Here at the top, I have our actual, kind of what's really going on diagram of sound waves. Remember, it's longitudinal waves. It's particles that are moving back and forth, back and forth. There's this chain reaction. They eventually reach your ears to go back and forth, back and forth. And I said before, instead of using these longitudinal waves, we're going to use transverse waves because they're easier to both draw and they're easier to see, easier to visualize, especially if we're going to talk about things like wavelength and things like that. So right down here, I have a speaker, a much simplified diagram of just a speaker. Here, the diaphragm of the speaker is right like this, and it goes in and out, in and out, in and out. The diagram would be right here. And let's say it's emitting a sound, of course, and let's say it's really boring. It's emitting a very constant sound. Well, we know speakers, they don't just emit one single wave once, they're emitting many waves. So here's one of the sound waves, again, using transverse. All right, just to make our lives easier, here's another transverse wave. We'll assume the volume staying constant. It's just a really boring, constant tone. Even so, this is kind of a pain to draw, to be honest. I have these waves here. I've only drawn 4, and already it's taking up a big chunk of space, so to speak. There's another way to represent waves, and that's where this term wavefront comes in. Right here, I have the crest of this wave, and here I have the crest, and here I have the crest, here I have the crest. If I was to draw a line, it should be straight, like that. That line is where I have all crests. Here's another spot where I have all crests. And here's another spot that I have all crests. And then there's one spot right here. As well, there's another spot right here. Imagine I just deleted these blue lines. What I have left in red, these are lines representing the crests. And this diagram is known as wavefronts, where I'm just drawing a line that is representing the crests of the sound waves. Now, if I'm representing the crest, let's make sure we understand from right here, this piece right here, all the way to this piece. What is this length? That's a wavelength. So from this to this red line to this red line, crest to crest, that's a wavelength. This is also a wavelength. This is also a wavelength. So when I just have wavefronts drawn, by definition, the distance from one red line to the next, because I'm always drawing them crest to crest, those are wavelengths. So I can pretty easily figure out the distance. I'm actually going to go in right here and I'm going to delete this diagram. I'm going to get rid of all of these, and I'm going to get rid of this. Now, speakers, when they emit sound, they don't emit sound just in a single direction. It kind of spreads out as it travels. Again, I would have like transverse waves going like that, transverse waves going like that, transverse waves going like that. Even more of a pain to draw. So instead, what you'll often see are wavefronts. Here I am connecting the crests. I know I only drew a couple. What I have in blue, these are wavefronts, and if I did a good job drawing those blue lines, they should be nice and evenly spaced. Again, the distance from wavefront to wavefront, that's wavelength. Now, to be honest, sound waves don't just travel in straight lines or even curved lines. If I have a speaker, it's traveling outwards in all directions. So here's a classic example. I stopped drawing those transverse waves. These are all wavefronts. Again, from here to here, that's a wavelength. And really, in real life, wave travels in 3 dimensions. So what you'd actually have are like spherical shells that are expanding. But these are moving outward just as the wave moves outwards. Remember, they are representing the crests of the waves, much easier to draw. And the distance from one line to the next, those are always wavelengths. In fact, you've seen this before, the classic 2000 and forward version of showing Wi-Fi, and so showing data, showing the radio waves that are being emitted. It's using wavefronts. Here's our classic Wi-Fi symbol. Those are wavefront diagrams that you're seeing. Okay, so remember this wavefronts because that's how we're going to see the Doppler effect come into play. To get into the Doppler effect, I actually want to do two things. First being remembering two things. First, the speed of sound is constant. Remember, it's around 340. It can change slightly based on the temperature of the air, the pressure, but in one given area, all right, in San Mateo, California, the speed of sound on a given day is going to be constant. Next thing to remember is the wave speed equation, V equals F lambda. And now let's realize what this equation means if the speed is constant. If this value right here on the left always has to be 340, then I have an interesting relationship between frequency and lambda. If the frequency of a wave decreases, the wavelength would have to increase because I always have to get to the same speed, that 340. So when one of these values goes down, the other goes up. If you know the wavelength of a sound wave is getting smaller, that must mean that the frequency is getting bigger. That's the only way that I could have a constant value. So now we have this inverse relationship between frequency and wavelength. When one goes up, the other must go down. That's using the wave speed equation and the fact that the speed of sound is constant. All right, still, before I actually get to the Doppler effect, I want us to look at a diagram that's going to work as an analogy that will help us better understand. I have three pictures here, three versions of someone throwing a ball. Let's just look at the top. I changed the background to white so it's a little easier to see. Let's say here you are, you throw the ball. You're always going to throw it at the same speed, the same V. And at some other point in time later, maybe a second later, the ball winds up right here. And for actually each of these three trials, the ball's always going to wind up, because we're throwing it at the same speed, this location, and they're starting at the same spot. Well, in case one, you throw the ball, after that 1 second, the ball's right here. Well, it's located some distance away from where you threw it. This is some delta x, right? This isn't too challenging. You throw the ball, after a certain amount of time, it traveled a certain distance. Well, now let's go down to example 2. You still throw the ball, and you still throw the ball at the same speed as before. So again, after 1 second, it ends up at this same location. But now imagine, right after you threw the ball, you lunged forward. You made a quick couple of steps forward. Well, right after you threw the ball doesn't know you're moving forward. It's going to move with whatever speed it was thrown with. We won't get into projectile motion right now. But the fact that you then lurched, you lunged, you quickly moved toward the direction of the ball actually means that the distance now between you and the ball, delta x2, is smaller, of course. After you threw the ball, you moved towards it. So there's less distance between you and the ball. Lastly, case 3. Again, we'll assume you're throwing that ball with the same speed. Okay, it travels after 1 second. It's at this location here. But now let's say you lunged away from the ball. So right after you threw it, you quickly turned and you started booking it to the left. Well, here you have a greater distance because you traveled in the opposite direction that wave was traveling. Now there's more distance between you. This is going to be helpful to understanding the Doppler effect. Okay? Well, I'm going to pull up a diagram here. Not that one, we'll do that later. Here I have a website. When I click, I have a spaceship. And this spaceship has a speaker. Imagine like a siren, like on an ambulance. And that siren is just emitting a constant sound. And you're seeing wavefronts that are propagating. You're seeing the sound waves move outwards. It's as simple as that. Yeah, I'll reset. Again, it's just stationary. Those wavefronts are moving outwards at the speed of sound. So obviously this is slowed down, but they're moving outwards. And the distance between these wavefronts, it's constant. Notice they're not changing over time because the speed of sound is constant. And the distance between two wavefronts represents the wavelength. All around, the distances are the same because those waves are just spreading out. Now I'm going to reset, and I'm going to give this rocket ship a little bit of forward speed. Now look at what's happening. It's the same as my diagram over here. The spaceship is of course emitting sound waves, but as those sound waves that are moving forward move forward, the spaceship is also moving forward. So like my diagram over here, you threw the ball and you lurched in the same direction. This distance between waves is smaller because the ship is moving in the same direction. Let me maybe make it a little more extreme. Aha! So the spaceship is moving after each sound wave. It moves in the direction of some of those sound waves. So what you see here are wavefronts that are more bunched up, closer together. If wavefronts are closer together, over here you have smaller wavelengths. And look at what's going on here. It's what's going on in diagram 3. In diagram 3, after the ball was thrown, after the waves were sent out, emitted, it moved away. The person moved away. The rocket ship is moving away from these sound waves. So I have larger distances, larger wavelengths here, smaller wavelengths here. So if I have a smaller wavelength, what is true about the frequency? Well, when lambda goes down, what did we say before? The frequency goes up. So here, when those wavelengths are bunched together, you hear a higher frequency. When you're over here, what's going on with those wavelengths? The wavelengths are getting bigger. If the wavelengths are getting bigger, the frequency gets smaller. So I have higher frequency sound on the right, in front of the object, lower frequency on the left. Let's listen to an example of this. That's the Doppler effect. When that fire truck is moving towards you, those wavefronts are closer together. Smaller wavelength, bigger frequency, higher frequency. When that truck passes you by, now all of a sudden you're experiencing bigger wavelengths or lower frequencies. Let's listen again. All because of this diagram. So let's get to our definition of the Doppler effect. Definition, the Doppler effect. I recognize you're going to hit pause to write this down. The Doppler effect is the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. And again, it's all about looking at when you have relatively small wavelengths, small lambda means bigger frequencies, and on the backside they're more spread out. So you have larger lambda, so smaller, lower frequencies. It's relative motion between the source of the wave and the observer. This is the listener. This is like the truck. All right, that's our definition. I have another diagram to show you. Let me start again. Here's our person. Here comes an ambulance. Again, it's sending out those wave signals. And again, because the ambulance is moving in the same direction, these are getting bunched up. The person's actually kind of going to blink at the frequency of the waves. They're hearing the waves at a certain frequency. And then when the truck passes by, to the side, don't worry. Now the truck, because it's moving away from the sound, there are bigger wavelengths. Bigger wavelengths, smaller frequencies. So you hear that classic high pitch then low pitch just because that object that's moving past you, when it's moving towards you, it's compressing those wavelengths, higher, bigger frequency. When it passes you by, lower, smaller frequencies. That's the Doppler effect. Okay? Couple things to keep in mind about the Doppler effect. First, it's talking about frequency, changes in frequency. It's not discussing amplitude. We're not talking about the volume of these sound waves. The ambulance gets louder just because it's getting closer to you. The Doppler effect is not telling you why it's getting louder. It's telling you why you have that higher frequency and then a lower frequency. So it's not about amplitude, not about volume. It's about pitch. It's about frequency. And two, I've never used the word acceleration in this video. Okay, in those two visuals, those animations, we did not need acceleration. It's just some type of motion. So don't think the Doppler effect requires acceleration. An ambulance moving at a constant speed, the speed limit, is also going to have that Doppler effect going on. So it does not require acceleration, just some kind of motion between the thing emitting the sound and the listener. Sometimes you might see a question that's using the Doppler effect like this. If you saw this diagram, what direction would you say this green dot is traveling? It must be traveling this way, to the left, because we're bunching up our sound waves here. Here's where we have those smaller wavelengths. Here are the larger wavelengths. So hopefully knowing wavefronts and the Doppler effect, you can discern the direction of objects based on the patterns you see. Okay, I'll leave you with just a meme. Thank you very much for watching. I guess it's not really a meme. All right, the Doppler effect. Thanks a lot.